Welcome back. So in our last explainer, we really dove into the theory behind hashing. Today, we're going to put that theory into practice with one of the most famous problems in all of programming, two-sum. But listen, this isn't just about getting the right answer. It's about seeing how a tool like hashing can completely flip the script on how we approach problems in the first place.
Okay, so let's get right into it. The real thing you're going to walk away with today isn't a chunk of code. It's a new way of thinking, a new mental model. We're going to see how a simple data structure, the hash map, can take us from a clunky, brute force method to something super elegant and efficient.
All right, here is our challenge. We've got a list of numbers, and we've got a target number, in this case, 9. The mission is simple. Find which two numbers in that list add up to our target. Now, you and I can see it's 2 and 7, right? But the real question is, how do we teach a computer to figure that out efficiently?
So let's start where pretty much everyone starts, the most direct, straightforward way you can think of. We're just going to check every single possible pair of numbers until we find one that works. This is what we call the brute force approach.
And this is what that thinking looks like as code. You see we have two loops, one right inside the other. The outer loop grabs a number, let's say it picks 2. Then that inner loop goes through the entire list all over again, pairing 2 with every single number, including itself. If a pair adds up to 9, great, we found it. It's simple, yeah? But you can probably already see it's not very smart.
Now, this mental model is totally natural. It's the leave no stone unturned strategy. It definitely guarantees you'll find the answer if it's there, but the price you pay for that guarantee is checking a ton of combinations that you just don't need to.
So why is this so bad? Let's get into it. First, we're doing the same work twice. We'll find the pair 2 and 7, and then later we'll find the pair 7 and 2. It's redundant, and worse, its performance just falls off a cliff as the list gets bigger. That's what we call O of n squared complexity. Basically, we're taking the long scenic route instead of a direct flight.
Okay, we can do a little better without changing our whole strategy. We're still going to check all the pairs, but let's just be a little more clever about it and get rid of some of that wasted effort.
And here's the fix. Look closely at that second loop. See how it starts from I plus 1? That's a tiny change, but it's a really smart one. By just starting one spot ahead of whatever number the outer loop is on, we instantly stop the code from checking a number against itself. And we stop finding those duplicate pairs. Much cleaner. So our thinking has evolved a little bit. We're not just blindly throwing things at the wall anymore. We're doing it in a more organized, careful way. But, and this is a big but, we're still stuck on the idea of checking every possible combination. And that's the real problem here. Even with our little trick, the performance is still O of n squared. We're scanning and rescanning. The fundamental issue is that our code has no memory. It's like it has amnesia. When it looks at the number 7, it has completely forgotten that it just saw the number 2, which is the exact number it needs.
All right, this is the pivot. This is the big moment. Let's just throw out our old way of thinking. Instead of scanning the list over and over again looking for a partner, what if we could just remember the numbers we've already seen? What if we could just ask our memory if we've seen the number we need? This right here is the hashing mindset.
This slide is the whole ballgame. On the left, that's the brute force question. It's all about scanning forward. But on the right, that's the hashing question. It looks backwards. For any number I'm on, it asks, hey, is the partner I need to make 9 times already in my memory? It's a total game changer. And this is the code that asks that new, smarter question. It uses something called a hash map, or if you're a Python person, a dictionary. And just look at it. There's only one loop, a single pass. That's the hashing mindset in action. So how does this magic work? It's actually super simple. For every number in our list, we first figure out what number we need to hit our target. Then we just check our hash map, our memory. Is that needed number already in there? If it is, boom, we're done. We found our pair. And if it's not, no problem. We just add the current number to our memory and move on to the next one.
This is the new mantra. This is the idea you need to burn into your brain. For every single element, you check your memory for its partner first. Only after you've checked do you then store the current element in memory for future numbers to look for. It's an incredibly powerful pattern.
So why is this so much faster? Well, first, we only go through the list one time. That's what O of n means. And the real magic of hashing, which we talked about last time, is that looking something up in the map, that's O of 1, which is basically programmer speak for instant. No nested loops, and we can stop the second we find an answer. So we did it. We solved 2-sum. But why does everyone, interviewers, professors, programmers, make such a huge deal about this one specific problem? It's because it's what we call a canonical example for hashing. What's a canonical problem? Think of it like the perfect textbook case. It's a single, clean, simple problem that manages to teach you all the important lessons of a much, much bigger idea. If you really, truly get how hashing solves 2-sum, you get the core of how to use hashing to solve a whole class of other problems. And this table just lays out our entire journey perfectly. We started with that check everything brute force mentality. Then we got a little smarter with check carefully, but we finally landed on the remember and jump mindset with hashing. And just look at that jump in complexity, from O(n) squared all the way down to O(n). That's not just a little better, that is a massive, world-changing leap in efficiency. So let's really spell out the lessons. 2-sum shows us exactly where brute force falls apart. It demonstrates the incredible power of an instant hash lookup. And it teaches us a classic concept in computer science, the time-space trade-off. We're using a tiny bit of extra memory, the hash map, to save a huge amount of time. And believe me, this is not a one-trick pony. This remember and jump pattern is a fundamental tool in your problem-solving toolkit. You are going to see this exact same way of thinking pop up all over the place, in more complex problems like 3-sum, counting up how many times you see an item, finding subarray sums, the list goes on and on. Learning this pattern unlocks so many other solutions. So, I'm going to leave you with this question to chew on. The next time you're looking at a problem and your first instinct is to write a nested loop and just rescan everything, stop. Take a second and ask yourself, can this be solved by remembering instead? You'll be amazed how often the answer is yes.